Alright, so we're going to continue talking about graphs and whether or not they're planar, and all the ideas that kind of get folded together with these questions. So kind of just as a reminder, we're going to talk about V being the number of vertices that a graph has, or let's say V is the number of vertices that a graph has. E will be its number of edges. All right, and the new thing is we're also going to count the faces it has. Okay. Now remember, there's some subtleties about whether or not a region's a face, but we've addressed those in the previous video, right? A region that is simply connected as a face, if you're working on a sphere or a board or a piece of paper, just check that your boundary has one component, right? But of course, if you end up on more exotic surfaces, then you have to check simple connectivity, right? So like if you're on one of these things with a handle, and you draw a region, you have to make sure that region is simply connected. Basically, that region will allow loops to close, right? Any loop you draw, you could close it. All right, but anyway, we're going to be counting these amounts. All right, the vertices and edges are really just intrinsic to the graph, but the faces come from how you put that graph on the surface, okay? And like I said, we often use the surface, the plane, but remember, I want you to transfer that to a sphere, right, like this. Remember that all of the regions are of finite size. All right, so let's try some things. All right, so first of all, let's look at the octahedron, which is the reason I brought this thing here. Okay, so I know it's not perfect to see in the video, but there's an octahedron, and it's a four-sided pyramid on top of a four-sided pyramid. This is one way of thinking about actually drawing it on a sphere. So this is where you're thinking about what a sphere might look like, might be pushed a bit. This is a sphere, and this is a sphere. The difference between them is their geometry. So this sphere has uniform curvature all the way around. These two spheres, so this dodecahedron, this octahedron, these spheres have pointy bits, right? They have points. And everywhere where it's not pointy, the curvature is actually zero. Well, the cardboard gets curved, but this curvature is actually completely flat, just like a piece of paper. And so the curvature actually is condensed in these vertices here. All right, we're going to use that as a tool later on, but right, so there's different ways of drawing a sphere. You could insist that a sphere have uniform curvature, and so this is your only definition of a sphere. But if you're a topologist, which is the mathematics of how things are kind of structured without looking at their curves, you would say all three of these are spheres. Right, and this is a sphere that's almost closed. Okay, and this is not a sphere, right? This is something different. All right, so looking at the octahedron, you can check out, and we can think of it as a graph being drawn on a sphere. But remember, we can just draw it on a piece of paper and put that piece of paper on the sphere. I'm kind of drawing this backwards. I may need to. I think I got it. You don't have to memorize how to draw these things. It's just a sort of an accidental skill from doing it too often. All right, so this definitely always takes a minute to realize that this is the octahedron. If you look at this thing, it has vertices all of degree 4, it has triangular faces, and one way of thinking about this is this sort of outside face is you just taking a look through here, so getting zoomed in, and then you're looking at the bar face, right? So if you look at the octahedron, if you look through a face and look at the opposite face, it will be upside down. So just like this one's upside down. It does take some imagination to do that. All right, so let's see. Let's count how many vertices we have. So in this case, we have 1, 2, 3, 4, 5, 6 vertices. Edges. You could just count them, but here's something you should start practicing. We have 6 vertices of degree 4. So if you add up the degrees, we get 24. And if you want the number of edges, we just divide by 2. So 24 divided by 2 is 12, which is way more pleasant to me than counting the edges. You could, but you don't need to. All right, faces. Let's enumerate the faces just for practice. So there's a 1, 2, 3, 4, 5, 6, 7, and don't stop there. Don't forget what you'd call the outside face. The book will call this the infinite region, or the infinite face, or the unbounded region, the unbounded face, some terminologies like that. But keep in mind, if you're doing this properly and putting it on a sphere, every single one of these 8 faces is actually identical in structure. When you put it on a sphere, this number 8 face is no different than the 1 face or the 3 face, structurally speaking. They're all triangles. It's just, you can think of this as actually a distortion of the actual thing, right? Alright, so we have 8. Let me write down 8 for that. Alright, so the Euler characteristic is where we want to start looking. We started spelling character. I got pretty deep in that word for us. Characteristic. Okay. Okay, and this is not an X. This is a chi, C-H-I, chi, and that's why the characteristic goes with this. There's also a topic in graph theory called chromatic theory, and so this notation gets reused for that. So you'll often need context to make sure that they're talking about a characteristic or an Euler characteristic instead of a chromatic number. But again, it's because both words start with CH, so you use this chi for that purpose. Alright, let's call this graph G. And keep in mind, there's more than just G. It's how I drew G that is also important. But we're going to calculate something called the Euler characteristic. And it's just attributed to Euler. And we're going to do something kind of strange. What we're going to do is we're going to put together these numbers in a specific way. So we're going to take the vertices, we're going to subtract the edges, and add the faces. Alright, so in this case, if we do it with our example, we get 6 minus 12 plus 8. So in this case, minus 6 plus 8 is 2. So the Euler characteristic of this graph drawn on a sphere is 2. Alright. Sometimes if we know it's already a planar graph, we could just be lazy and say the Euler characteristic of the graph is 2. But you intrinsically mean that you drew it on a sphere if you say that. If it's not clear what surface you're putting it on, then you're being fairly careless with what you're saying here. So you could include more data here, right? Like G on a sphere or something like that. Alright. Let's try this again. Let's try it with a cube. Okay. Now I'm going to draw a cube without edge crossings. The reason is I want to put this thing on a sphere, right? And I want to count vertices. I have 8 of those. Edges. I do the sum of degrees thing, right? So 8 times 3 is 24 divided by 2, I get 12. 12 edges, very similar to this thing here. In faces, one good example of what the cube is remember, a cube has 6 faces, so it's harder to forget, right? You wouldn't say a cube has 5 faces. Cube has 6 faces. So I turned it into a 6. Right, let's try this again. So let me just say Euler characteristic of a cube. We have 8 minus 12 plus 6. This is also 2. Okay. Now you can try another planar graph, whatever planar graph you want. So I'm going to try one more. This time, let's be a little more creative, right? So maybe I'll start with this square shape. Maybe I'll add an extra edge, so you won't see this sort of thing in the book. So keep in mind, this is like extra. So I have a multi-edge here. Maybe I'll even add a loop. And let's go off and do something like that. And maybe add like a little triangle over here or something, right? So have some fun with it. You can do your own too. Just make sure you don't have any edge crossings and make sure it's connected. Very important that it's connected and no edge crossings. So you can do another example. And you can do a bunch of these, right? You could just pause the video after we do this one and try a bunch of examples of your own creation. Alright, I'm going to count the vertices and edges, of course, but let me go ahead and enumerate the faces. So that's done. I'm going to use a contrasting color. Let me switch this orangish color. Okay, so the area between these two edges is a face. Same thing over here. Looks like a face here, right? And then you just don't want to forget there is an outside face, right? It's just another face. Alright, so looks like 5 faces. Alright, so let's get the number of vertices. 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices. I have no trick for counting these edges, so I just have to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And faces, 5. Alright, so let me call this thing H, just give it some sort of name, and calculate its Euler characteristic, V minus E plus F. So 8 minus 11 plus 5 equals 2. Alright, hopefully you're starting to see a trend, right? This can't be a coincidence that we keep getting 2. And if you want to try it, pause and try some more examples, you should continue to get 2, but see if you can break that. Okay, so this is true. This is a theorem. All right, we'll need a little bit of space to describe this theorem properly, because it's really a theorem about putting graphs on a sphere without edge crossings, and the graphs need to be connected. There's a few qualifiers here that are really important. But once you get that, you can claim and we can prove that we always get 2. Okay, so we'll prove that. But this is really fun to play with. The first time I saw this, it was just mind-boggling that you always get 2. You have no recourse to do anything else. So you should notice that, okay, that means that the vertices, edges, and faces are not just completely flexible, right? If you change one, you're going to have to change something else to make this work. So like if you increase the number of vertices, then this whole edge-face dynamic, right, it has to adjust so that you still get 2. You can't get away from it. Just like the sum of degrees has this, but this seems much more profound than the sum of degrees, right? The sum of degrees theorem seems to just be basic, has something to do with the edges having 2 ends, and this seems to be something more profound than that. It is profound, but it is not hard to prove. That's one thing that's super cool, but it is something specific to the sphere. So we'll get to this and we'll make this more dignified, but this is a property of the sphere. It's not exactly a graph theory thing. The Euler characteristic of the sphere itself is 2. Okay, and the way this is usually approached, from if you were taking this in a topology course or another math course that is really focused on this, would be to start with the sphere and then decompose it into faces, edges, and vertices. This process is often given a slightly different name, but it's the same thing we're doing. This decomposition is constrained in this way. It's pretty neato. Now this surface, this torus, this thing with the sphere with the handle sort of thing, this is a different Euler characteristic. If you want to give it a try before I do it in another video coming up, you go for it. But you do have to make sure you just divide the torus into faces, right? So the edges and vertices not a problem, but make sure you divide it into faces. Okay, so I hope you think this is cool. Feel free to play with it a little bit. Have fun with it. Try to be creative. Keep in mind, if you do get something besides 2, I would suggest that you've done something, you've either miscounted your vertices, edges, or faces, or your graph is not connected, or you have an edge crossing in there. Remember, so you just need to satisfy these basic rules and you'll always get 2. Okay, so I'll see you on the next one.